In this video, I want to talk about hybrid search. Hybrid search was built based on the idea that for a long time we were using keyword search to search our data, and it was performing well. But then semantic or dense search was introduced, and we were able to achieve a whole new level of performance. But our semantic search generally does not generalize very well to new domains. If our data is very different from what our embedding models were trained on, then semantic search may perform worse than something like keyword search. So hybrid search seeks to solve that problem by combining keyword search with semantic search and trying to alleviate some of the disadvantages of each. If we wanted to implement a hybrid search pipeline, we would take our document and use a smart tokenizer to create a sparse vector and then insert that into a sparse column in our vector database. We would then take the same document and use an embedding model to create a dense vector and insert that into a dense column. We would then be able to search both columns and then re-rank the results. And this has all kinds of advantages. It's perfect for situations where contextual specificity is extremely important, which means we're searching for specific keywords, but we still want some of the performance improvements of semantic search. It's also useful when we haven't had the chance to fine-tune an embedding model on our specific data. In those cases, keyword search performs well, but keyword search mixed with semantic search can perform even better. Our dense vectors are high-dimensional vectors containing mostly non-zero values. So every single value is going to have some meaning associated with it. And it could represent all the different semantic meanings, relationships, and attributes of a document and capture a lot of the complex relationships between the features. And it's good for comparing our query vector and our document vector semantically. Once we use an embedding model to generate our query and document vectors, we could then use a similarity metric to compare them, like Euclidean distance and cosine similarity. Sparse vectors, on the other hand, are high-dimensional vectors that contain mostly zero values, which means that the few non-zero elements are going to be highlighted. And the sparse vector represents each unique token within a document. It uses the BM25 algorithm to match keywords and find the most relevant document to our query. The sparse vectors are created with tokenizers. Tokenizers break text into smaller subsections, like words, subwords, or even characters. And we use neural tokenizers in many cases. For example, BERT Tokenizer Fast can take your document and split it into a lot of different tokens. And we use those tokens to create a sparse vector. And then once we have a sparse vector, we could actually create a mapping between every single unique token and the number of times we actually counted that token. Sparse search is typically done with a BM25 algorithm. It's an algorithm that was developed in the 70s for document retrieval, shows great performance, and ranks sparse vectors based on a sparse query vector. BM25 decides which documents are most relevant by checking how often search terms appear and then adjusting for document length and considers how common terms are in the entire collection. And that's what the algorithm on the right does. And at a high level, what this means is if we have a query, for example, like what are neural networks? Then words that are going to be very common in our documents, like what are going to be weighted way less or even weighted at 0 than the words neural networks, which are much rarer. KDB.AI uses an inverted index to facilitate BM25 searches, which means we map terms to the documents they appear in. And this means we could very quickly identify all the documents that contain a given term. Once we insert new data into our sparse column, all the underlying BM25 statistics have to be updated so we maintain an accurate search. Hybrid search takes an inbound query, creates a dense vector, creates a sparse vector. And then we could do two searches. We could do a BM25 search and a dense vector similarity search. Take the top K results from each, and then we re-rank the results based on an alpha parameter. So we can also, in KDB.AI, we could run dense and sparse search independently. We don't have to combine them with hybrid search. And this allows for some very interesting search pipelines. For example, one disadvantage of hybrid search is that it uses this alpha parameter and it kind of mixes sparse results and dense results in a way where the ordering often gets messed up, because things that can have a very high keyword score but a low semantic score would be rated worse than things with a medium keyword score and medium semantic score. And this is often not the best way to compare results. So when we're doing re-ranking, another option is we could take the top K sparse results and the top K dense results, and we can re-rank with a re-ranker instead of using an alpha parameter. And a re-ranker will have a much better understanding of the relationship between the query and document vector. Re-rankers actually have a much better understanding of keywords as well. And this means our re-ranked results might be better than just using an alpha parameter. So there are both options that you could try. A re-ranker is going to be, of course, slower. Re-ranking with an alpha parameter is instantaneous. But these are both options to consider. So with KDB.AI, you could search individually, which might be useful as an option to a user as well. If you're searching with semantic similarity, you're going to get extremely different results than when you're searching for keywords. So for example, if you're searching for companies, often you could try searching with keywords, see if you get good results. Search semantically, see if you get good results. And then you could use hybrid search as a default to get the best results in general. When we are doing hybrid search, there's a very important hyperparameter that we have to optimize, and that's our alpha. And our alpha is how much priority we give our sparse index and how much priority we give our dense index. So an alpha that is high or close to 1 means that we're going to give our dense scores higher priority. And an alpha that is closer to 0 is going to mean we're going to give our sparse scores higher priority. In KDB.AI, you could actually have multiple indexes. So you could have multiple dense indexes, you could have multiple sparse indexes, and you could assign a granular score to every single index. And these scores should add up to 1. There's also these additional hyperparameters of B and K that you can set when you instantiate your sparse index, or specifically your BM25 index. Or you could actually tune at runtime. Now, in practice, I recommend tuning your alpha parameter because it's much more important than B and K before you tune B and K. But if you do need that extra granularity for B and K, which is rare, then you could actually tune it at runtime. So you could set the correct B and K that you need. Now, B is document length, impact, and relevance. So in general, documents that cover a very specific topic, lots of specific topics, should use a lower B. And documents that cover many different topics should use a higher B. And K is term saturation. So what that means is how fast do additional instances of a term not give that document an additional boost in score. So in practice, tuning this B and K isn't that important. You could kind of just get away with using the default, but tuning the alpha is very important. Although you could also get away with just using the default alpha of 0.5, but especially as you have multiple indexes, you can have over 2 indexes in KDB.AI, then this alpha becomes extremely important. And you could also do some very interesting things here. For example, when you, instead of doing hybrid search, you could search with one index and re-rank with the vectors from another index, or you can do a sparse search and re-rank with vector, or you can make a search and then do some clustering after that. So there's all these different things and different ways to weight your search results. But an easy way to get started is just to do hybrid search with a sparse and dense index, and in most cases that is going to improve your search performance. And below we have actually a code snippet, and this code snippet shows that we have a sparse index, we have a dense index, and we're assigning a weight, a B, and a K to the sparse index, and we're assigning a weight to the dense index. So since the weight for the dense index in this example is so high, what this means is that it's going to give a very much a priority to the dense scores. So the sparse scores or keyword scores are not going to be as important for this search. There are lots of different use cases for hybrid search, and it's generally areas where our embedding model isn't really trained on this kind of data. One is legal document search. If we're searching through a vast database of legal documents, often our embedding models aren't going to understand a lot of the specific legal jargon. And for that, keyword search is going to be extremely useful, and hybrid search is going to be more performant than keyword search depending on your alpha parameter. For human resources and recruitment, often we're looking for specific keywords and specific skills and titles, where keyword search is extremely important, and hybrid search is going to generally perform well. We can also create a content recommendation system where we not only find similar content semantically, but we also want to add an understanding of specific terms the user is interested in. We could also do customer support automation. For example, for searching our knowledge base or documentation, often there's going to be specific terms that are specific to your company or your documentation that the embedding model won't completely understand. And for that, hybrid search is going to be extremely effective. Hybrid search is also a good add-on for a RAG. If we're creating a RAG pipeline with hybrid search, it's going to look very similar to a typical RAG pipeline. We have our data, we chunk it, instead of embedding it, we embed and tokenize it, and insert our vectors into our sparse and dense columns in KDB.AI. And then when we have a user prompt, we embed and tokenize the user prompt. We do a hybrid search on a database, we return the relevant data, and then we can insert it into a large language model. And the interesting about large language models is if you're using an agent, they can dynamically decide whether you should use a keyword search or a semantic search based on the query. And this is something that is actually really interesting because they can do this extremely quickly. And I've seen APIs that have a neural parameter where you could decide, do you want a neural search? Do you want a semantic search? Do you want a hybrid search? And LLMs can understand based on the query and your specific data or a description of your specific data, which one of these is going to perform best. So this is something that can be considered. But in general, when you're doing RAG, you want the best possible results fed into your LLM. And hybrid search is something that can improve the accuracy of your retrieval. And that's it. That's all I want to talk about today. Thanks so much for watching, and I'll see you in the next video.